All right, good afternoon, everybody. Here is your next lecture video, the Chapter 9 video. And we're going to try something a little bit different this time. I'm going to try and go through the actual lecture slides just like I would in class, so you can follow along and not have to have separate things and whatnot. But as we go through these slides, what I would like you to do is whenever we approach a question that would be on one of those worksheets that I hand out in class, I'd like you to hit pause on the recording, try to work out the problem, and then press play again and follow along and see how you did. Okay, so Chapter 9 is all about drawing molecules, basically. And the type of drawings that we are doing in this chapter are called Lewis structures, okay? Now, with Lewis structures, there's a thing called the octet rule. And what that means, the octet rule is this thing right here. And what it means is that atoms are stabilized by having a full set of 8 electrons in their valence shell. When you are dealing with nonmetals, like chlorine, oxygen, nitrogen, things like that, what they do is they take those valence electrons that they have and they share them, so that basically it's like communal resources and that sort of thing. So in that first example here with chlorine, each one of these chlorine atoms has 7 valence electrons all by itself. But if they share those 2 electrons in the middle, if they share them, now each one of those chlorines feels like it has 8 electrons. So if I sort of zoom in here, that left-hand chlorine feels like it has all of those electrons. And the right-hand chlorine feels like it has access to all of those electrons. Okay? So this is the way nonmetals make structures, is they share electrons in order so that everybody feels like it has 8. Let's take a look at this oxygen molecule down here. So each one of these oxygens has some electrons to play with. Okay, each one of the oxygens by themselves has 6 electrons. But if they share those extra electrons, now each oxygen feels like it has a full 8 electrons. Right? It has access to 8 electrons, so it feels like it's full. Okay? When we show how these electrons are shared, what we do is we draw lines, and each line represents 2 electrons. We can imagine that there's an electron on the end of each one of those lines, just like that. Okay? So looking at these nitrogens when they pair up, looking at the focusing in here, we can imagine that each one of those lines is just like there's an electron on each end of the line. Okay? And each one of those nitrogens has access now, because it's sharing electrons with the other one, it has access to 8 electrons. There are 8 dots that it has access to. Okay? And that's the goal. Everybody wants to get to that 8 because it's a very stable place to be. Okay? So when we look at our first one here, and this is where you would like to pause the recording, try this out. But I'm going to explain it first. So after I explain it, then give it a shot. Okay? So the question says, do these atoms fulfill the octet rule? So looking at this drawing, I'm going to zoom in here. Imagine that there is a dot at the end of each line. Okay? At the end of each line, there's a dot. Okay? So if I want to focus on one particular atom, I'm going to sort of zoom in on one thing. Okay? Everything that oxygen has and is connected to, it has access to. So right now, that oxygen has 1, 2, 3, 4, 5, 6, 7, 8 dots around it, okay, that it has access to. Okay? Now, hydrogen being what it is, because it's so small, hydrogen can only ever have 2 electrons. I'm going to write that down real quick. hydrogen can only have 2 electrons. Okay? You will never see hydrogen with extra electrons. Okay? You will also never see hydrogen with double bonds. Okay? That's never going to happen. Okay? So in this part over here, in this part of the box of the table where it says valence electrons, what it's asking is how many electrons does a particular atom have access to? Okay, so if I were looking at this particular oxygen, I would say that it has 2 bonds, it has 2 sets of lone pairs, and 8 valence electrons. It has access to 8 electrons here. Okay, so put me on pause, fill out the table. Stop. Put me on pause, fill out the table, and come back to me when you're done. All right, so hopefully, once you've worked all this out and come back and hit play again, we get these answers. There should be 4 electrons or 4 bonds on that carbon. So let's sort of zoom in and take a closer look. So there are 4 bonds on that carbon. We can say 1, 2, 3, 4 bonds. Okay. There are no lone pairs. There are no dots all by themselves on that carbon. And if I imagine that there's a dot at the end of each bond, everything that carbon is connected to, okay, it has access to 8 dots. 1, 2, 3, 4, 5, 6, 7, 8. So we would say 8 valence electrons there. Okay. Right? So this nitrogen, let's take a look at him. Right? So that nitrogen has 1, 2, 3 bonds. It has 1 lone pair. And it has access to, 1, 2, 3, 4, 5, 6, 7, 8 electrons. Okay. Now the hydrogens, let's take a look at a hydrogen set. So the hydrogen has 1 bond, and it has access to both of those electrons. It can only ever have 2 electrons connected to it. Okay? Right. So here's another place where I'd like you to give me a pause and write down these rules somewhere that you're going to be able to find them. Okay? Or copy paste this into something else, but these are the complete rules for drawing Lewis structures. And you're going to want these because if you follow these rules every time, you will get the right answer every time. Okay? So give me a pause, make a copy, write them down, whatever you need to do. Right? So hopefully you've got that all recorded. So let's talk about these steps. So the first step is to add up all the valence electrons. So if I have a molecule like CH4, okay, we're going to know that carbon has 4 valence electrons, and each hydrogen has 1 valence electron, so 4 times 1. So that means that there is a total of 8 valence for this particular molecule. Okay. So step 2 says to draw a simple structure. Okay. So I'm going to draw a simple structure. Okay. Step 3 says to subtract 2 electrons for every bond that I've drawn. So if I started with 8 valence electrons, I don't know what that was. Okay, 8 valence, and what I've done is drawn 4 bonds in my molecule. So I'm going to subtract 8 electrons for what's in the bonds. Okay? Or let me rephrase that. 8 electrons in the bonds. Okay? So I've used up all of my electrons. So that takes care of step 4 and step 5. Now step 6 is our last step. Okay, and we're going to make sure that all the atoms have at least an octet. Now remember that hydrogen is different. Hydrogen's special, so it can only ever have 2 electrons. So it's not going to have an octet. Carbon, on the other hand, should have an octet. So let's take a closer look and imagine that we have a dot at the end of each bond. I'm going to change color here real quick. So everything that carbon is connected to, we're going to focus our attention on. All right? So inside that circle, there are 8 dots. Okay, that means that carbon has a full octet. Right? The hydrogens are just fine because they can only hold 2. Right? So our correct structure for that molecule looks like this, right? Normally we wouldn't actually have the dots in at the ends of the bonds, but it really doesn't matter. Okay. All right, so let's take a look at, so this is sort of a simplified version of things, of the rules for drawing Lewis structures. All right. So let's take a look at our example here. All right. I'm going to start with the CS2, just because I think it's a better example, right? And then we'll come back to the CH2O. But this would be a place where you can pause me, work on the problem, and then come back and see how I did it. All right, so following my pattern, right, following my rules, I'm going to start with the CS2, right? So step 1 says to count up the valence electrons. What is the total number of valence? My carbon has 4, and each sulfur has 6, so 2 times 6. All right, 2 times 6 is 12, plus another 4 means that I have 16 valence electrons to put in my drawing. Okay, so I'm going to put carbon in the middle, and I'm going to draw something that's symmetrical. Okay, starting with drawing a symmetrical thing is a better way to go. Okay, if you draw something like this, that's not symmetrical, and it's going to get you in trouble. Okay, it's going to make your life really difficult. So when in doubt, err on the side of drawing a symmetrical molecule. Okay, so now step 2 says that I'm going to, or step 3 rather, says that I'm going to subtract 2 electrons from my total for every bond that I've drawn. So I've drawn 2 bonds here. That means that I subtract 4 electrons for what's in the bonds. Okay, 4 electrons in the bonds means that there are 12 left to put in my molecule. Right, so the next step says to put those electrons on my outside atoms first to complete their octets. So right now, each of those sulfurs has access to 2 electrons. So I'm going to give each one 6 more to complete their octets. All right, fill up my outside atoms first. Okay, and we draw them in pairs. Okay, we don't draw them sort of evenly spaced around. All right, we draw the electrons in pairs. That's why they're referred to as lone pairs. All right, so now I've put 6 electrons on my left-hand one and 6 electrons on my right-hand one, so that I've used up 12, which means that I have no more left to put in my molecule. Okay, so the step where I don't have anything to put on my central atom. Okay, so my last step is to check my octets. Okay, so right now, my sulfurs have access to 8 electrons. They are happy. The carbon, on the other hand, only has access to 4 electrons right now, right? 2 for each of those bonds. So what I'm going to do is I'm going to borrow electrons from my outside atoms and make more bonds. So I'm going to take these, let me use a different color. I'm going to use these electrons, and I'm going to borrow those and make them come over here. Okay, and I'm going to make an extra bond with those. And I'm going to leave it in this crazy color just so you can see that those are the ones that I borrowed. Okay, so now my sulfur still has 8 electrons. It's still happy. There's 2 in each of the bonds, so that makes 4. And then it has 2 lone pairs. There's 4 more. So that sulfur still has 8. Now my carbon has 6, so we're getting there. Right? So again, erring on the side of doing something symmetrical, I'm going to borrow 2 from this side and bring it in. Okay? And I'm borrowing from my outside atoms only. Okay? So now if I check, my carbon has 8 electrons. If I zoom in a little bit, I can say that and use a different color. So my carbon has 2, 4, 6, 8 electrons around it. And my sulfurs have 2, 4, 6, 8 electrons around them. 2, 4, 6, 8. Okay? So there is my finished drawing for CS2. Okay? So let's come over here and take a look at CH2O. Okay? Right, first step is to total the valence electrons. So there's 4 for the carbon, 2 times 1 for the hydrogen, and 6 for the oxygen. So 4 plus 2 is 6, plus another 6 gives us 12. Okay. Now I'm going to draw a symmetrical molecule. Now, the rule says that the atom that goes in the middle is the one that is either farther left or farther down, or both, okay, out of the group, excluding hydrogen. Hydrogen's never playing by the rules. So between carbon or oxygen, carbon is farther to the left on the periodic table. So I'm going to put carbon in the middle, and I'm going to draw a symmetrical molecule, or as symmetrical as I can get. Okay? So now I'm going to subtract 2 electrons for each of the bonds that I've drawn. So I've drawn 3 bonds, so I'm going to subtract 6 for what's in the bonds, meaning that I've got 6 electrons left to put in my molecule. Now the hydrogens are done. They already have their 2. I can't put any more on the hydrogens. So I'm going to put electrons on my oxygen to fill that octet. Oxygen is my outside atom. Okay, so now oxygen has an octet, and I've just used up the last of my electrons. Okay. So now there's nothing left to put on my central atom, so I'm all done putting electrons in my molecule. So my last step is to check the octets. So right now the oxygen has access to 2, 4, 6, 8 electrons. The carbon, it has access to just 6 right now. So I'm going to borrow some electrons from my oxygen. I'm going to take those away, and I'm going to make an extra bond. All right? So now my oxygen still feels like it has 8, and my carbon has 8 now. And then my hydrogens have as many as they can have, which is 2. Okay? All right. So in our examples here, here's our finished product, and here's our finished product. Okay? So let's take a look and do a little practice with totaling up the number of valence electrons. Right? This is a little practice with your nomenclature too, which is useful. All right. So phosphorus trichloride has a formula of PCl3. Right, phosphorus has 5 valence electrons, and each chlorine has 7. So 3 times 7. 3 times 7 is 21, plus 5 means 26. Okay. So moving along here. Again, reminding you to give me a pause when we get to these questions so that you can figure things out. Now, when we have ions, so for example, Cn minus, right? Remember, electrons are negatively charged. So if I have a minus sign, that means that I have to add one extra electron to my total number of valence. Okay? So looking at the Cn minus ion, there should be 4 here for the carbon, 5 for the nitrogen, and 1 more for that negative sign. Right? So we'll find that there are 10 valence electrons for the cyanide ion. All right, moving along. So which of these is a correct Lewis structure for sulfur dichloride? Right? Put me on pause, see if you can figure it out. All right, so if you have resumed me, let's take a look at each one individually. So looking at A, this A guy. So each one of those chlorines has access to 8 electrons right now. Imagine, if you will, remember there's a dot at each end of the line. And that chlorine has access to all of those. Okay, so chlorine has an octet. Great, cool. What about the sulfur? Right now the sulfur only has access to 4 electrons. Right? So, not a valid Lewis structure. Everybody has to have at least an octet. Okay? All right, let's look at B. Now, everybody has to have at least an octet, and everybody in row 2 of the periodic table cannot have anything more than an octet. Okay? But both of these elements, chlorine and sulfur, are below row 2, so they're allowed to have more than an octet, but they should have at least an octet. The problem is with the number of electrons in this drawing. Let's look. All right, so sulfur dichloride, SCl2, sulfur has 6, 2 times 7 for the chlorines. 14 plus 6 means that there should be 20 electrons in this drawing. Right now there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay? So that's not a problem. I thought it would be a problem. Sort of going through the possible reasons for this to be a funny drawing. Okay, so what else might be the problem here? All right. Sorry for the dead air. Let me think. So I know that there is a problem with a thing called formal charge, but I don't want to talk about formal charge yet. We'll get to formal charge later, but I will say that this is not the correct drawing. I'm going to come back to you guys. All right. This is very much like being in class, isn't it? Okay, so D is going to have a similar problem. 2, 4, 6, 8, 10, 12, 14, 16. Except D does not have the right number of valence electrons. Okay, so right now D has 2, 4, 6, 8, 10, 12, 14, 16 electrons in the drawing. Okay, so D is also not a correct Lewis structure. So what we're going to find is that C has the right number of valence electrons, and when I get to formal charge, I'll explain why this one is a better drawing. Okay? but I'm not quite ready to explain formal charge yet. Okay. So for CS2, okay, let's take a look at these various versions of CS2. So all the elements in the second row of the periodic table, they must follow the octet rule. They cannot have more than 2 electrons. Okay, so more than 8 electrons. So right away, I can look at this particular drawing and see that that carbon has 2, 4, 6, 8, 10, 12 electrons around it. Carbon has to follow the octet rule. That right-hand sulfur only has 6, right? It has to have at least an octet. Okay, so this one's a no-go. The other 3, let's see. CS2 should have 4 plus 2 times 6. That's 12, so 16 valence. So let's see, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. This one has 20. Okay. 2, 4, 6, 8, 10, 12, 14, 16, 18. This one has 18. Right? And then number B there, 2, 4, 6, 8, 10, 12, 14, 16. This one has the right number of valence electrons. And it has the correct octets for everybody. Okay. All right, so how many lone pairs of electrons are on the central atom of the chlorate ion? So chlorate, hopefully everybody remembers, chlorate is ClO3 2 minus, or just 1 minus, excuse me. ClO3 minus. Okay, so let's draw the Lewis structure for the chlorate ion. I'm going to give you time to pause and give it a shot. All right, so if you're coming back, let's start at step 1, which is total the valence electrons. So there's 7 electrons on the chlorine, and then 3 times 6 for the oxygens, and then 1 more for that negative sign. Okay, so that's 18 plus 7 is 25, plus 1 more means 26 valence electrons. All right, now I'm going to draw a symmetrical molecule. All right, and I'm going to subtract 2 electrons for each bond that I've drawn. So minus 6 electrons in the bonds means that there's 20 electrons left to put on my molecule. I'm going to fill my outside atoms. I'm going to fill their octets first. All right. So that took care of 18 electrons, which means that I have 2 electrons left to put on my central atom. Okay, so that takes care of all my electrons in my drawing. All right, so to answer the question, how many lone pairs of electrons are on the central atom of the chlorate ion? There is 1 lone pair. All right, now if I'm going to be sticklery about the rules, whenever I'm drawing a Lewis structure for an ion, especially a negative one, I'm supposed to finish it off by putting the whole thing in a big bracket and then putting the charge of the ion on the outside. Okay? And that's just by convention. That's the way they do it. Okay? Thus, there's 1 lone pair on the central atom. All right, so let's take a look at another example. I'm going to give you some time to pause me and come back to it. So this should be the nitrite ion, so there should be a negative NO2 minus there. Okay, so for NO2 minus, let's look at our number of valence electrons. There's 5 valence for the nitrogen, 2 times 6 for the oxygens, and then 1 more for that negative sign. So that's 12, plus 1 is 13, plus another 5 means 18 valence. Okay, so I'm going to draw my structure, making a symmetrical structure. All right, and between the two of those, the other reason that the nitrogen is in the middle, between the two of them, nitrogen is farther left on the periodic table, so it's the one that goes in the middle. Okay, so I'm going to subtract 2 electrons for the bonds. Means that I've got 14 left to put on my molecule. Fill my outside octets first. Okay, so that takes care of 12 electrons, meaning I've got 2 left to put on my central atom. So we go there. Now I've put all of my electrons that in my molecule. Now my last step is to check my octets. So right now, both oxygens feel like they have access to 8 electrons. Great, they're cool. But my nitrogen feels like it has access to 6. So in order to fix that, I'm going to borrow from one of my oxygens and make an extra bond. And it doesn't matter which one. I can borrow from the right one or the left one. They're both exactly the same molecule. Okay? Oh, and I forgot my brackets. Should keep my brackets. I always forget that step. Okay? So what this does is it brings up an interesting topic. Okay? Because both of these drawings, the left one and the right one, are exactly the same molecule. They're both correct Lewis structures. Okay? So what that means is that they are what we call resonance structures of each other. Okay? So we draw these Lewis structures so that we can keep track of how many electrons are in which place. But the reality is that both of those drawings are correct simultaneously. So it's very easy to think that that double bond is shifting back and forth between the left side and the right side, almost like flipping a light switch on and off. The reality is what is in this box here is that really those are 2 1.5 bonds instead of a single bond and a double bond. Okay? But we only ever draw things this way. We never draw them this way. Okay? We talk about how that is, and we acknowledge that this is the reality, but when we're drawing Lewis structures, this is our preferred method. This one right here. Okay? So whenever there are multiple correct drawings that you can show, and usually it's when there's a double bond and you could put a double bond either left or right or top or bottom, that's when you have resonance structures. Okay? So next we're going to get into, now I want to encourage you to do a lot of practice with drawing Lewis structures. Okay? It takes a bit of time to get accustomed to using those rules. Now, if you use the rules, you will be correct every time, okay? So before we move on, before we move on to doing this, I want to come back to this topic of the topic of formal charge. Okay, so give me 1 second here. I'm going to add a page so I can talk about formal charge. All right, so let me think. I had an example from earlier today. All right, I'm going to put you on pause and I'm going to find a good example and come back.